Hello students, welcome to EPG Pathshala. I am Rima Gupta from University of Delhi and today we are going to talk on module pressure sensor, and this is from the paper Semiconductor Materials and Devices. So after completing this module, the students will be able to understand what is a pressure sensors, and pressure sensors are basically of two types. One is capacitive pressure sensors and another one is piezoelectric pressure sensors. So students, we will be reading about the piezoelectric pressure sensors and capacitive pressure sensors one by one. We will be able to differentiate between them and the fabrication process for both of them. A pressure sensor measures pressure typically of gases or liquids. So a pressure is an expression of the force required to stop a fluid from expanding and is usually stated in terms of force per unit area. A pressure sensor usually acts as a transducer. It generates a signal as a function of pressure imposed. Such a signal is electrical, and it was the cutting-edge technology that allowed the versatile sensors to be used in a wide range of settings. The altitude pressure sensors are also used in aircrafts, satellites, weathers, and even barometric applications. The flow sensors are based on differential pressure measurements to measure the liquid flow. Level or depth sensing applications include submarines, drivers, and water towers. Leak sensors measures the pressure decay. When a pressure sensor delivers a voltage signal, the signal is converted to actual units of pressure. So the conversion formulas are based and they vary on the types of the sensor used. So typical pressure sensing application range from common everyday users and life support to exotic investigational devices. So the devices addressing measurements as blood pressure cuffs, sleep apnea detection, respirometers, anesthetics controls, air concentrations, and other applications benefits from advancing sensor technology. So many technologies span those used to manufacture pressure sensors and including semiconductor piezoresistive, strain gauge, microelectromechanical, that is MEMS, mechanical deflections and vibrating capacitors can be used. So we will read one by one the types of pressure sensors and their fabrications. Pressure sensors. In the present era, MEMS-based sensors are being used in every field of life, industry, commercial sectors, as well as in defense sectors. Due to the latest advancement in microscale fabrication technology, micropressure sensors are being fabricated utilizing the MEMS-based diaphragms for a wide pressure range varying from ultra-low pressure to very high pressures. With the advent of silicon-based devices, traditional metal diaphragms are being replaced by silicon dioxide, silicon nitride-based membranes structures. These technological derived sensors reduce the cost to a great extent. The pressure sensors used in the market for commercial applications are based on different principles such as piezoresistive, capacitive, optical, piezoelectric, and many more. Amongst all these principles, piezoresistive and capacitive based pressure sensors are widely used. There are various advantages being offered on integrating pressure sensors with the functional piezoelectric thin film. The advantages of utilizing piezoelectric film for pressure sensors include high pressure sensitivity, low power consumption, low noise levels, large dynamic range, low temperature sensitivity, which is very good as compared to piezo-resistive pressure sensors. So students, now let us discuss about the working principle of pressure sensors. The schematic of pressure sensors based on MEMS structure using piezoelectric thin film is shown in the figure on the left hand side of the slide. It consists of two parallel plates, that is top and bottom electrodes, separated by a piezoelectric thin film in between. With the application of applied pressure, either the thickness of piezoelectric layer or the dielectric constant changes, which is directly related to the applied pressure. The schematic, which is shown in the figure on the left hand side, gives the design of the pressure sensor based on change in dielectric constant of the piezoelectric layer on application of applied pressure. As pressure is applied from the top side, due to the movement of diaphragm, the capacitance of the piezoelectric layer changes. Therefore, the complete sensor is bonded on a Pyrex glass, which gives strength to the fabricated sensor, besides providing the pressure compensation using a specialized design process. Now here comes the types of pressure sensors based on design modification. So the first one is absolute pressure sensor. This sensor measures the applied pressure relative to perfect vacuum, that is 0 psi, encapsulated within the pressure. In this case, the fabricated MEMS pressure sensor chip having a diaphragm is bonded to the glass in vacuum such that there is vacuum between the cavity and glass. The pressure sensor is shown in the figure on the left hand side of the previous slide, and it is shown that it is an absolute pressure sensor. Such devices are used for atmospheric pressure measurements as manifold absolute pressure sensor, cabin pressure control in launch vehicles and satellites, etc. are being used. Now comes the second is gauge pressure sensor. This sensor measures the pressure relative to atmospheric pressure, and there is no vacuum between the glass plate and the sensor chip fabricated over the membrane as compared to absolute pressure sensor. A tire pressure gauge is an example of gauge pressure sensor, and a zero pressure measured using a gauge pressure sensor means that the applied pressure over the diaphragm from the top side is same as that of atmospheric pressure. The gauge pressure sensors are used for blood pressure and pressure measurements. The vacuum sensors are also gauge sensors designed to operate in the negative pressure sign. The third one is differential pressure sensor. The differential pressure sensor measures the difference between the two pressures on each side of the diaphragm, one from the top and the other one from the cavity side of the MEMS structure. The bonded glass consists of a hole through which the pressure may be applied. Technically speaking, most pressure sensors are really differential pressure sensors. For example, a gauge pressure sensor is merely a differential pressure sensor in which one side is open to the ambient atmosphere. The differential pressure sensor are used in high pressures oxidation systems to maintain the oxygen pressure ranging from 1 to 10 atmospheres inside the quartz tube during the oxidation of silicon. In such systems, the other ambient of the tube is maintained at slightly high pressure of nitrogen, and this pressure difference is monitored during differential pressure sensors. Differential pressure sensor can be used to measure the pressure drop across an oil filter. They are also used to measure the flow in pressurized vessels in the non-major, or you can say a required manner in the defense applications. So depending on the applications, one can use any one of the above mentioned pressure sensor. The pressure sensors are majorly used in number of applications like gas sensing, brake boosters, diesel engines, blood pressure measurement systems, and heartbeat measurement systems. They are also used in space propulsion applications, flight control systems, hydraulic system which have manifold air pressure, the pressure management system, and many more. It has wide range of applications in the field of aerospace and defense. It is also used for pilot input force measurement and servo loop feedback. Moreover, the pressure sensing products can be utilized for the applications including military trucks, unnamed vehicles, and armored vehicles, etc. They have also been utilized for the applications in fuel monitoring, compressors, transmission delay lines, hydraulic pumps and motors for delay of government and fast for variety of government vehicles and the test equipments. So students, till now we have discussed about the pressure sensor and its working principle. Now comes MEMS based pressure sensors. So there are basically two types of pressure sensors. One is capacitive pressure sensor and second is piezoelectric pressure sensors. So in capacitive pressure sensor, students, you all can see a diagram on the front side of the slide, and you can see that this type of pressure sensor is capacitive. So the capacitive sensors employ two thin membranes enclosing a cavity forming a capacitor where the deformation on one side of the membrane would result in capacitance, and the schematic of pressure sensor is shown below. So students, now let us discuss the fabrication process for the pressure sensors step by step, which are shown below with the schematic representation. So the first step is cavity and bottom electrode formation or fabrication. The silicon needs to be cleaned thoroughly following the standard process of cleaning including RCA1, RCA2 and piranha cleaning. So this cleaning should be carried out before the processing of the wafers. The cleaned wafers will be carried out for the lithography, that is photolithography, for forming the cavity and bottom electrode. The photolithography includes an spin coating of photoresist, baking alignment and exposure followed by development of the pattern. The exposed photoresist will be removed from the selective area of the wafer followed by the etching of silicon dioxide and silicon. The bottom electrode will be deposited over the patterned wafer for the desired thickness. After deposition, the residual photoresist will be removed using acetone or IPA. Here IPA is called isopropyl alcohol. Now the next step is the polysilicate glass. The polysilicate glass, that is PSD layers, will be deposited, that is the sacrificial layer, using ICP chemical vapor deposition technique, which covers the entire cavity. The patterned wafer will be polished during the chemical mechanical polishing such that the thickness of polysilicate glass matched with the thickness of silicon dioxide layer. Now, the PSD layer is present only over the metal electrode in the cavity, which you all can see in the figures. So after this, the photolithography will be carried out again for patterning of the processed wafer for the membrane layer formation. The membrane layer formation will be deposited using physical deposition technique over the patterned photoresist coated wafers, and extra photoresist will be removed during the process using acetone. A different set of photomask will be used for patterning the wafer for removal of PSD. Here PSD is polysilicate glass. For removing the PSD from the cavity, some holes will be patterned in each cavity such that the sacrificial PSD layer will get removed easily. After the removal of PSG, the processed wafer will be patterned in such a way to deposit the top electrode over the membrane using conventional photolithography technique through desired photomask as figured. Finally, the fabricated devices will be characterized, diced, and packaged in appropriate material, that is, a metallic header. Now students, we have discussed the process flow for the fabrication of capacitive pressure sensors. Now let us see the schematic for the same. So students, you can see a schematic for pressure sensors, and on the right hand side of the slide, you all can see the color coding meaning. So the gray color corresponds to silicon substrate, green portion correspond to silicon dioxide layer over silicon, blue color corresponding to PSG, dark green color correspond to membrane layer, dark blue color correspond to metal, and orange color correspond to the photoresist. So students, you can see on the left hand side of the diagram that first the SiO2 coated silicon was taken over which the photoresist was deposited using spin coater. After that, a set of mask is used such that we get some part uncovered and some part covered with a photoresist. After this step, the etching of SiO2 has been carried out on Si wafer such that the grooves become more deeper on the areas where there is no photoresist. After this step, or after the formation of grooves, the layer over SiO2, that is photoresist, is being removed. So students, we get the polishing condition after the PSD deposition. So in case of polishing, the extra photoresist should be removed and it becomes smooth. Finally, a membrane layer is deposited on the fabricated device. Now moving towards the right hand side of the diagram, you can see the second part or the above part of the capacitive pressure sensors. So in this case also the same procedure has been taken and followed. So in this case again the photolithography technique has been carried out, but in this case the membrane layer is deposited. So over the membrane deposited layer, the photoresist was again coated. Again the photolithography was carried out and etching was done. After etching, the removal of photoresist was there, and after removal of PSG, the membrane looked like this. The third part is deposition of metal and PR. So To make the cavity of metal and PR, what we did, we have optimized again the set of mass to get the desired signature or pattern using photolithography technique, and etching was further carried out. At the end, the photoresist was removed such to get the complete fabricated device. Till now, we have discussed about in general the process flow for the fabrication of sensors. However, there is another approach which may be adapted for the realization of capacitive pressure sensors, that is, using the wafer bonding technique and SOI wafers. Pressure sensors using both the techniques will be fabricated simultaneously. The schematic is shown on the next slide, where the steps are shown in a process and the process adopted for the fabrication is detailed here. Firstly, the silicon wafer will be cleaned thoroughly using standard wafer champions. The silicon dioxide will be grown on silicon wafer using thermal oxidation technique. Then, the conventional photolithography process will be used for patterning the silicon dioxide, as you can see in the next slide. When the patterned wafer will be bonded with the SOI wafer, so here SOI means silicon dioxide insulator, SOI wafer using anodic bonding technique. Then the silicon and silicon dioxide will be etched during SOI wafer from the front side as shown in the next slide. The top electrode and the bottom electrode will be patterned in the same manner as mentioned in previous case. Once it is fabricated, the characteristics will be studied using laser Doppler vibrometer and semiconductor characterization unit. So devices at the end were prepared and diced and packaged. So students, we have already discussed about the process flow for the fabrication of capacitive pressure sensors using the wafer bonding technique and SOI wafers. So let us understand it once again using a schematic. So students, on the right hand side you can see the figure for the complete fabrication process. On the top you can see the first figure, which is SiO2 coated silicon wafer over which the photoresist has been deposited. So in this case, orange color is the photoresist, light green color is the silicon dioxide, and violet color correspond to silicon wafer. After that, a desired photomask has been chosen, and using conventional photolithography, the pattern has been transferred on the wafer. So you can see, after using a photomask and conventional photolithography, the pattern has been converted and designed on a wafer. So you can see, after development of a wafer, there are some parts which are uncovered, that is, which are not covered by the photoresist, and there are few parts which are covered by photoresist, which are represented by orange color. So after this, the wafer has been etched, that is, the etching of silicon and silicon dioxide has been performed. So you can see in the figure, the green portion which is not covered by the photoresist has been removed, and some part of silicon, that is some part of violet color, has also been removed. So after etching, the photoresist which is covering the SiO2 is also removed, such that we can deposit the bottom electrode using any physical deposition technique. So after the deposition, you can see the area which is not covered by SiO2. So on those areas, the metal electrodes are there. Now in the second step, we are taking the SiO2 wafer. So you can see on the second column of the figure on the top side. So on the top side you can see the SOI wafer. So SOI wafer is insulator, oxide, insulator, that is silicon, silicon dioxide, silicon wafer. So we have processed the wafer in the same way as we did previously to deposit the top electrode. So top electrode will be the metal only. So after processing it, the SiOi wafers with top electrode and the before processed wafer with the bottom electrode where we performed etching of silicon and SiO2 were bonded together. So after bonding, you can see that there are cavities which are present between top and bottom electrode. So this complete device is the capacitive pressure sensor, and it is obtained by removal of insulator in the SOI wafer. Now the next pressure sensor is piezoelectric pressure sensor. Piezoelectric sensors use the piezoelectric effect to measure the change in pressure. So students, you can see the schematic of the pressure sensor which is shown in the slide. In this case, zinc oxide is taken as piezoelectric thin film on the N-type silicon wafer using 100 orientation. Now comes the fabrication steps for the piezoelectric pressure sensors. The fabrication steps are shown here. Zinc oxide, as we have discussed earlier, is taken as piezoelectric thin film. So the fabricated device will be characterized, diced and packaged. The steps for the fabrication are: first, the N-type silicon wafer with 100 orientation will be taken for the fabrication of piezoelectric pressure sensors. The silicon dioxide will be grown on both sides of silicon wafer using thermal oxidation technique, and the photolithography will be carried out to open the window on one side of the oxide silicon wafer. Next, after photolithography, the silicon dioxide and silicon will be etched using wet etching technique. After successful etching, the remaining oxide layer remains on the wafer, which will be removed as shown in the figure later on. The fresh oxide layer of silicon will be grown on the processed silicon wafer using thermal oxidation technique, and the bottom electrode, that is bottom metal electrode, will be deposited on the selective area of the silicon dioxide having the silicon membrane, which was fabricated using photolithography and physical deposition technique. Furthermore, a sequence of silicon dioxide, zinc oxide and silicon dioxide layers will be deposited over the bottom metal contact. Also, the top electrode will be deposited over it for taking the electrical connections. Prior devices or prior to device fabrication, individual SiO2 and zinc oxide layer will be deposited exhibiting the desired properties. Finally, the processed wafer will be bonded on the glass substrate using wafer bonding technique to develop the desired piezoelectric pressure sensors. Now students, here comes the process flow for the fabrication of piezoelectric pressure sensor. So same as capacitive pressure sensor, a wafer has been taken, silicon wafer has been taken, which is represented by violet color, and over that the silicon dioxide has been deposited on both top and bottom side, which is represented by green color. After that, the conventional photolithography has been performed and some windows have been opened such that we can do selective etching of the silicon. So after that, the membrane has been formed, and over the membrane, when membrane is formed, the SiO2 is completely removed and again coated such that to get a smoother surface. So after getting the smoother surface on a silicon membrane, which is coated by SiO2, an electrode has been deposited over it. So after depositing the electrode, The piezoelectric layer, that is zinc oxide, has been deposited, and then again top electrode has been deposited using photolithography on a selected areas of the piezoelectric material. So this is the piezoelectric pressure sensor, where the changes will be observed due to piezoelectric effect, whereas in the previous case that was capacitive pressure sensor, where there was no piezoelectric layer, so the changes which are occurring is due to change in capacitance. However, after the fabrication of such devices, the dicing and packaging plays a major role. The MEMS based pressure sensors, it can be capacitive or piezoelectric, can be fabricated by employing photolithography technique, which we have discussed earlier. In order to make the whole process cost effective, the large number of pressure sensors can be fabricated simultaneously on a single big silicon wafer. The sensor fabricated in this way can be diced to separate each of them separately. Pressure sensors can then be packaged and finally they are ready for use. So students, let us now summarize what we have learned in this module. Students, first of all, we have discussed about the pressure sensors and its application. Then we have moved on to the types of pressure sensors. So basically we have discussed about two types of pressure sensor. One is capacitive pressure sensor and another is piezoelectric pressure sensor. So in capacitive pressure sensor, the way of fabrication is different from that of piezoelectric pressure sensors. In capacitive pressure sensors, a cavity is formed without any piezoelectric layer and a cavity is surrounded by the top electrode and the bottom electrode. So the changes in the pressure will result in the change in capacitance, resulting in the generation of voltage. The second is the piezoelectric pressure sensor. In piezoelectric pressure sensor, we are using a piezoelectric layer, that is zinc oxide in the present case, and the zinc oxide here is surrounded by the top and bottom such that the charges can be collected as a result of piezoelectric effect. Thank you.